So good morning, ladies and gentlemen, and welcome to today's lesson. Today we start with the quality of service topic titled QoS service models. So what is quality of service and why do we need to learn about it? So the continuous development of the network and the increasing network scale and also traffic types can cause internet traffic increase and the risk of traffic congestion in your network. When you talk of traffic types, we are referring to traffic types such as data, video, and voice. So they have different requirements. They have different requirements in order to ensure communication quality. So when traffic congestion occurs, services encounter, if you've been to networks where the network is so low, so slow, so long delays, and it can also cause even packet loss, so that you are completely unable to access the internet from that particular network. So that is caused by congestion. So as a result, service deteriorate or even become unavailable. Therefore, a solution to eliminate traffic congestion on the IP network is urgently needed. Now, one of the best ways to eliminate traffic congestion is to increase the network bandwidth. However, as you might have already guessed, increasing the network bandwidth also comes at a very high cost, which might be invisible. So QoS technology is used to solve the problem. So with limited bandwidth, this technology uses guaranteed policies to manage network traffic and offer what we call differentiated services. So by the end of this chapter, you should be able to. Alan, please assist.
Upon completion of this section, you'll be able to, 1, understand the factors affecting QoS.
Yes.
2, be familiar with the QoS service models. 3, understand the implementation of the DiffServ model.
DiffServ or differentiated service model. Thank you very much, Alan. Now let's begin by looking at the traditional network communication quality problems. So what is the problem? What is the problem with traditional networks? Now, you see, at this particular point here, we have a 10 Mbps link. Now, we have all these people sending data, and they're coming at that particular, they can be able to come in to the router at a maximum of 10 Mbps. So this is the enterprise branch network. Now, that particular router is connected to the headquarters via a one link. Now, the one link is a serial link that can offer a maximum of 2 megabits per second. Now, you see, when the aggregated data comes to this particular point, you see we are going to have what we call congestion. We are going to have congestion. And some services which require or are sensitive to delays, such as voice or video. You see this guy is using teleconferencing. So video, voice, they are very sensitive to congestion. Now, this problem is a result of the traditional way of forwarding data, which is done in a manner we normally refer to as FIFO or FIFO. So first in, first out. First in, first out manner. So in the traditional network, this is how data is forwarded. So what happens is, well, whichever packet comes in first is the one that goes out first. So that cannot guarantee service quality to delay sensitive data, like live video or voice. Now, this particular way of doing things is actually referred to, as you're going to see, the best effort model. So this is the best effort, first in, first out, also known as BE. So this particular model is not appropriate. Now, as you're going to see, we have several factors that affect communication quality, and the different traffic types have different they actually have different requirements in terms of delay, what we call jitter, what we call packet loss ratio, and also what we call reliability. So in this particular chapter, we are going to understand some of this. We're going to understand all of this, characteristics, and know how then to cater for the different traffic types. Okay, so let's move on. So as you can see, the data flow is moving from the enterprise to the branch. So the data flow is 10 Mbps, but when it gets here, it gets a bottleneck. A blocked point. So we're going to have congestion at that particular point because of the difference in bandwidth. Okay. So let's now look at the factors affecting network communication quality. No, let me just see. Okay. I thought there was something I hadn't said, but it's okay. I think I've said everything. Okay, so let's look at the let's look at this. Now, in your network, we have different traffic types that have different requirements. So we said you can have voice, like the IP phones. You can have video, like the teleconferencing videos, IPTV, etc., video on demand. You can have protocols such as FTP, and you can have the normal internet traffic, like email, HTTP, and so on and so forth. Now, each of these has a different requirement in terms of the bandwidth, the delay, the jitter, and the packet loss ratio. Now, in terms of bandwidth, voice requires low bandwidth, but it is very sensitive to delay and to jitter. If you can lose a few packets, not very sensitive to that, it's okay. But delay and jitter, no. So I'm going to tell you what jitter is just in a moment. With videos require high bandwidth. They're sensitive to delay and jitter, otherwise the video will hang. But again, with video packets, it is okay if you can lose some packets. Okay, then we have some protocols. So we have protocols that, like FTP, that are not very sensitive, for example, to delay and jitter, but you cannot lose the protocol packets. So their packet loss ratio demand is high. Then we have the normal internet traffic, like emails. So emails, web pages, they don't require a lot of bandwidth. They do not have a very high demand when it comes to delay or jitter, but it has to arrive the whole of it. So the packet loss ratio requirement is quite high. So in the next slide, we should now understand some of these parameters that can affect communication quality. So the first one is network bandwidth. So one way to improve communication quality in our network is by increasing the network bandwidth. by increasing the network bandwidth, as we read in the foreword. The problem with that is that it is very costly. It is very expensive. Now, let's look at this example and understand what we call the maximum bandwidth. What we call the maximum bandwidth. Now, when we send data from the enterprise branch to the enterprise headquarters, what we call the maximum bandwidth is actually the bandwidth, the minimum bandwidth on the transmission path. The minimum bandwidth on the transmission path. You see, when this guy is sending this message, so we're sending this message to this guy. So when you're sending it from your device to your gateway, the speed is 100 Mbps. When the gateway is sending to the egress router, it is 10 Mbps. When this router is sending over the serial link here, the maximum bandwidth here is 256 kbps. When it gets to the ingress router of the enterprise headquarters, you see we have 2 Mbps there, and in fact here we have 1 gig. But what we refer to as the maximum bandwidth, BW max, is actually the minimum. This particular value, the minimum bandwidth. So however much you might increase the bandwidth within your internet, if you don't consider this, you're still going to have delays which might affect your communication quality. Now, we've been talking of bandwidth. What is bandwidth? So as you can see, bandwidth is actually represented in megabits per second. So S there is for second. So bandwidth refers to the data amount that is transmitted in a unit time. The unit time we are talking here about is 1 second. So when you talk of 100 Mbps, it means that on this particular interface, we can be able to transmit 100 MBs in 1 second on this particular interface here. When we talk of 10 Mbps here, most likely on one of that interface, 10 Mbps. So that is what bandwidth is. The maximum amount of data that we can transmit in a unit of time. Okay, so I've already told you that to improve your network communication, you can increase bandwidth. That's one of the strategies. The problem with this, associated with higher costs. So how else then? How else then can we be able to improve the communication quality in our network? Now, the other factor other than bandwidth that can affect communication quality is delay. So network delay. So we need to understand what network delay is and the different types of delays that we have. Okay. So you can see here, this guy is sending a hi message to this guy here. Then this guy receives it after 2 seconds. So hi, then this guy receives it after 2 seconds. So that is what we call actually the network delay. So the network delay is simply the period of time that it takes to transmit a packet from the source to the destination. From the source to the destination. Now, this particular delay is actually affected by several types of delays that you need to understand. One of them is called the transmission delay. The transmission delay, as you can see here. So you see, the transmission delay is actually the amount of time it takes to transmit that particular packet on the interface. So this kind of delay actually depends on the type of media that you're using. So what kind of media are you using here? Are you using fiber? Are you using Ethernet? Uh, or what are you using here? So it depends with that, and it also depends on the transmission distance. So those two factors. So transmission delay depends on those two factors, the type of media that you're using and the transmission distance. Now, after that packet has arrived on the router, for example, it encounters what we call a processing delay. A processing delay. Now, as we know, when the packet arrives, the router has to check through its routing table. Hey, do I know this destination network? Do I have it? Do I have it on my routing table? So that is what we call the processing delay. Really, the amount of time that the router takes before it puts that particular packet on the queue. So the packet has arrived, you have to check. You have to check about that packet. Do I have it? If I have it, then what's the next hop? So through which interface am I supposed to forward it out? So then it's going to place it on a queue. So that is what we call the processing delay. Amount of time it takes actually for the router to place that particular packet on the outbound interface queue. Now, as we've said, the packet is placed on the queue after we've identified the next hop. Now, that queue introduces another type of delay called the queue delay. So this is simply the waiting time of the packet in the queues. Then, other than that, we have what we call the serialization delay. Serialization delay. So, as you know, the interconnection between different routing devices on the network might be using different types of connections. For example, frame relay, PPP, and so on and so forth. So data has to be formatted in a certain way before it's forwarded on a particular medium. So that is what we're calling serialization delay. Serialization delay. So this is the amount of time that it takes to send the first bit of a packet to the last bit of a packet. Now, serialization delay depends on the link bandwidth and also the packet size. So that is what we call the serialization delay. So all these delays, the sum of all these delays is what now sums up, for example, to these 2 seconds. And that is what we call network delay. Network delay. As we've said, certain types of traffic, such as live video and voice, are very sensitive to delay. Now, the other factor that is closely related, to delay is jitter. In fact, jitter is actually a result of delay. Now, when we are sending a message, when we are sending a message from our machine, the message is broken down into packets. Fragmentation. The message is fragmented into packets of particular sizes, for example. So it's me, comma, but, like that. So that is how the packets are fragmented and sent out on the internet. Now, these particular packets cannot reach to the destination with the same interval, because they might encounter different delays periods during transmission. During transmission. So generally, this particular difference, so you see, like, this one is arriving after 50 milliseconds, this one after 50, this one 10 milliseconds, depending on the different network conditions during transmission. This one after 40 milliseconds, this one after 90 milliseconds, this one after 90 milliseconds. So that is what we call jitter. Jitter is simply the difference the difference in delay of different packets during transmission, packets of the same communication. So jitter occurs because end-to-end delays of each packet are different. End-to-end delays of each packet are different. When that happens, then jitter is going to occur. Now, as we said, for example, voice data is quite sensitive to jitter. In fact, the word they use for live video services like what we are using to learn right now and voice is that they are zero tolerance to jitters. Why? Because if the delay is not consistent, then that is when the voice, the communication is not going to be continuous. So it can cause a lot of problems. So video, voice services, live video, and real-time voice services, they are zero tolerant to jitters. Now, of course, as you might have already guessed, smaller. For example, if we have delays that are 50 milliseconds, then we have a higher probability of jitters occurring. But smaller delays, for example, if it was consistently at 10 milliseconds, then we will minimize jitters if we have smaller and consistent delays. So it is important again to mention that jitter is affected by delay, and a small delay indicates a smaller jitter. So I hope you remember that. Then we have what we've been calling the packet loss ratio in the previous slide. Packet loss ratio. So packet loss ratio really is the amount of packets that are lost. The ratio between the amount of packets that are lost to the ones that arrive to the destination. You see, this guy is actually sending a message. I send a file to you. But during transmission, packet loss occurs, and this guy is not able to get something there. So I just send, I didn't hear you, to you. So that is what packet loss can result in. So we said, for example, for voice and for live video, you can have some packet loss. So that's why sometimes when my internet connection is not very good, then you hear my voice breaking. Really, what's happening is packet loss. What is happening there is packet loss. So with voice and video, like what we're using now, you can tolerate some packet loss. But for protocol packets, it is quite sensitive to packet loss. But even more importantly, for web, HTTP, and also email, it has to arrive the whole of it. So they are quite sensitive to packet loss. Okay, so let's understand. We have three scenarios that can lead to a packet loss, or 3 points where packet loss can occur. So a packet can occur during transmission. So on the particular media that you're using, a packet loss can occur. So a packet loss can occur because maybe the link has gone down. Packet loss can occur because of interference from the external environment and other interferences that can occur on a particular type of media. So that's one of the points where packet loss can occur. The other one is during processing. As we've said, when the packet comes in, the router has to process it. The CPU has to check the routing table, identify the next hop, then place it on the queue for that particular next hop. Now, if packets are coming in at a very high rate than the CPU can process, then some packets might be dropped. So packet loss might also occur during processing. As you're going to see, Packet loss can also occur during queuing. We're going to look at different queuing mechanism. We're going to look at a phenomenon we call the tail drop, where if the queue has reached its maximum limit, then any other subsequent packets coming in are automatically dropped. So generally, those are the three areas where packet loss can occur. So packet loss may occur in each phase during transmission. Okay. So now let's look to the solutions to improving network communication quality. So if we are saying that just increasing bandwidth is not feasible, then what are the other solutions to improving network communication quality? So the first one, again, the first one is known as the best effort model, the BE model. So on the network where best effort model is used, you can increase network bandwidth. So that's one of the strategies. Or you can upgrade network devices in order to improve network communication quality. So those are the two things that you can do. Now, when you increase the network bandwidth, what are the advantages? So the advantage of doing this is that it eliminates the bandwidth bottleneck. It also reduces the serialization delay. Remember, we said serialization delay depends on the bandwidth of that particular interface and also the size of packets. And it can also reduce or prevent packet loss. So those are the advantages. Disadvantages: high costs, high costs, high costs. So that is a disadvantage. The other one is upgrading of network devices. As we said, things like packet loss can really occur here if you're receiving packets at a faster rate than you can process them. So packet loss is going to occur. So you can also upgrade your network device, which might also come with better interfaces, better CPU and memory. So the advantage of this, problems such as the processing delay, queue delay, and packet loss can be prevented. Disadvantage, again, costs are high. And device replacement causes service interruption risks. So replacing a device, especially on ISP's networks, on the core network, is not a very easy thing to do. It's quite involving. So that is what we call the best effort model. So the best effort model, of course, just uses FIFO, first in, first out. Okay, now the second model is what we call the IntServ model. IntServ is integrated service, integrated service model. So what is this? The IntServ model uses this protocol called RSVP, Resource Reservation Protocol. RSVP. So devices run some protocols to ensure communication quality of key services. Now, the integrated service model works in a very easy way. So you deploy a protocol, for example, the resource reservation protocol. So what happens is, for example, when this telephone wants to communicate, it actually sends an RSVP packet to the router, informing the router that, hey, I need you to reserve for me 63 kilobits per second bandwidth. Then the router will respond, okay, okay, if it's available. If it's not, then you see the router maybe will respond otherwise. So that is what happens in the entire stream of communication. So this router again will request for the same amount, like that, until the entire bandwidth is reserved for this particular communication. So the advantage of this, it can provide bandwidth for delay sensitive data in order to ensure communication quality. The disadvantage, normally the implementation of RSSVP or any protocol that is used for resource reservation is quite complex. And the other problem is that when no traffic is sent, then the bandwidth is still occupied or reserved exclusively. So for example, when these guys are not talking, maybe they've decided to put themselves on a hold a little bit. So the entire bandwidth is still reserved for them. So no one else can use that particular bandwidth. So bandwidth usage is low. The other problem is that all the nodes along the communication line must support RSVP, must run, actually support and run the resource reservation protocol. So for all those problems, the integrated service model is rarely used. So if this is rarely used, then what really is used? What is used is what we call the differentiated service model. Differentiated service model. So because the implementation of the integrated service model is complex and bandwidth usage is low, differentiated service model is used to ensure the communication quality of key services. Now, differentiated service model is also an interesting concept here. The traffic is classified into multiple types. So as we've said, in our network, we have live video, we have voice, we have the normal data, web, email, etc. So we classify different types of traffic. Then different actions are defined for each type of traffic. So these actions, of course, are defined depending on the characteristic of this particular traffic type. So we are looking again at delays, how sensitive, packet loss ratio, bandwidth requirement, etc. So that is what happens. Okay, now we have where we are using, when we are forwarding data based on the differentiated service model, is normally referred to as differentiated service domain. Differentiated service domain. Then, of course, we have the differentiated service edge node. So the edge node really connects to the differentiated service domain and another domain that is not aware of the differentiated service. So for example here, every packet is just coming in. So this particular area in the enterprise branch and also here, they're not forwarding using differentiated service. So it's not a differentiated service domain. So when it comes in, that particular device where it's coming in from is what we call the edge node. Then we have, of course, the differentiated service nodes. They're the ones that interconnect other devices within the differentiated service domain. Okay, so that is it about the differentiated service model. So let's look at how this happens. So let me go back. So you see the black broken arrow there. We have data from 3 types of users. We have live video, voice, and lastly we have normal data. So when they come into the DS edge node, they are classified So classify packets at the network ingress and remark the priority of packets. So we change the priority of packets. Now, once we've changed the priority of packets, the DS nodes are going to map the priorities of these packets to a locally defined class of service values. So that happens until that particular data leaves the until that particular data leaves the differentiated service domain. Okay, so number 3 here, send packet to the buffer queues based on the quality of service values. So we're going to see the different types of queues and their priorities, and implement differentiated services based on the scheduling mechanism between the queues. So we're going to look at that. So simply why we are remarking them and with different priorities is so that we can schedule them differently. We can schedule them differently. So in the coming topics, we're also going to look at the different types of queues and how they are scheduled. Okay. So this is just a comparison between these 3 models. So with best effort, the implementation is simple. Simply means you do nothing. Does not require any configuration. It's the default. First in, first out. Problem with this, cannot differentiate between different service flow. So delay sensitive traffic might not work well here. Then we have the integrated service model. So provides end-to-end quality of service and ensures the bandwidth and delay. So because it reserves that particular bandwidth end-to-end, so we cannot have delays here. Problem with this, as we've seen, it needs to trace and record the status of each data flow because of the protocol. So the implementation is complex and the scalability is low, and also the bandwidth usage is low because sometimes the network is going to be idle. The bandwidth is going to be idle. Then, so we've also mentioned that this is rarely used. So the one that is mostly used is differentiated service model. It does not need to trace the status of each data flow, occupies few resources because it does not really use a protocol, and has strong extensibility. In addition, this model can implement differentiated services. That is, it's able to identify the different service flows and classify them. So this needs to be deployed on each node. You have to configure and are high requirements for technical personnel capabilities. So it's also not very easy to configure differentiated service model because you need to configure the remarking, the classification and remarking, as you're going to see in the next topic. So that is the end of this particular chapter. Can I have a volunteer to take the first question, another person to take the next one? James?
Number 1, which are quality of service models? All of them are quality of a service model.
Thank you. Are you able to also mention the factors that affect network communication quality?
Yeah.
Which one and which one? Can you remember?
Network bandwidth. Jitter.
Yes.
Network delay.
Yes.
And the other one.
Anyone else? Someone can assist you. Which one is he forgetting? Owen? Alan?
Packet loss.
Packet loss, exactly. So packet loss ratio. Thank you very much.